Picture a hot piece of metal glowing from red to white-hot yellow. For centuries, physicists thought they understood this. Classical physics could predict planets and projectiles, so explaining glowing objects seemed simple, but their equations predicted something absurd. As objects got hotter, they should emit infinite high-frequency light, ultraviolet, X-rays, even gamma rays. If true, lighting a campfire would unleash a deadly cosmic blast. This failure was called the ultraviolet catastrophe, a sign that something was deeply broken in physics. The trusted rules led to impossible conclusions. The universe clearly wasn't a seething cauldron of infinite energy. The old view saw energy as smooth and continuous, like a beach seen from afar. But up close, reality is made of grains, individual pieces. Scientists were forced to abandon the comfort of classical physics and leap into the unknown. The ultraviolet catastrophe was the crack in the foundation, demanding a new map of reality. The stage was set for a revolution. The world of smooth certainty was over. The universe was about to reveal its hidden structure. The old map was wrong. It was time to draw a new one. The quantum era was about to begin. Enter Max Planck, a cautious German physicist facing the ultraviolet catastrophe. In 1900, he proposed a radical fixed energy comes in tiny, indivisible packets, quanta. Imagine energy as coins, not a continuous flow. You can have 1 penny or 2, but never 1.5. This idea instantly solved the catastrophe. High-frequency light required expensive packets, so ordinary objects couldn't emit them. Planck's math matched reality, but he thought it was just a trick. Then, Einstein took it further. In 1905, he explained the photoelectric effect. Only certain colors of light could knock electrons from metal. Bright red light did nothing, but even dim blue light worked. Einstein realized light itself is made of quanta, photons. A blue photon is like a baseball. A red one, a ping-pong ball. Only the baseball can knock the electron free. Light was both a wave and a particle. Planck's desperate idea was a fundamental truth. The revolution had begun. The universe was quantized. Energy came in packets. Light was a particle. The old rules were shattered. Physics would never be the same. Light as a particle explained some mysteries, but another experiment showed light was a wave. The double-slit experiment revealed interference patterns, proof of wave behavior. So, is light a wave or a particle? The answer, both. This is wave-particle duality, a core idea of quantum mechanics. Light travels as a wave of possibilities, but when measured it lands as a particle. Then came Louis de Broglie, who asked, if waves can act like particles, can particles act like waves? He proposed that everything, electrons, atoms, even you, has a wave nature. For big things, the wavelength is tiny and unnoticeable. For electrons, it's significant. Experiments confirmed it. Electrons fired at crystals created interference patterns, behaving like waves. The universe is a symphony of particle waves. Everything is a wave of possibility until observed. The solid world is just the surface of a much stranger reality. Reality is not what it seems. The quantum world is a shimmering sea of possibilities. Atoms weren't indivisible, they had parts. J.J. Thomson imagined the atom as plum pudding, but Rutherford's gold foil experiment shattered that. Most particles passed through, but some bounced back, proving a tiny, dense nucleus existed. Electrons orbited this nucleus, like planets around the sun. But classical physics said orbiting electrons should radiate energy and spiral into the nucleus. Atoms should collapse instantly. Niels Bohr saved the atom by combining quantum ideas with Rutherford's model. Electrons could only occupy specific orbits, energy levels. As long as they stayed in these orbits, atoms were stable. When electrons jumped between levels, they absorbed or emitted photons with energy matching the gap. This explained why elements emit specific colors, atomic fingerprints. The atom was no longer a miniature solar system, but a quantum machine. Stability came from quantum rules, not classical ones. The universe's building blocks followed strange, new laws. Atoms glowed with color because of quantum jumps. The quantum atom was born. The world was made of energy levels and leaps. The old models were gone. Bohr's model worked for hydrogen, but struggled with complex atoms. The next leap: abandon neat orbits entirely. Heisenberg's uncertainty principle set a limit: know a particle's position, lose track of its momentum, and vice versa. This isn't about bad tools, it's a fundamental property of nature. Schrödinger's equation described particles as waves of probability, not definite paths. Electrons became clouds of probability, fuzzy, three-dimensional shapes called orbitals. The electron doesn't exist in a single spot, but as a spread-out possibility. The universe is not a clockwork machine, but a game of cosmic dice. Reality is governed by probability waves. You can't ask, where is the electron, any more than you can pinpoint a note in a symphony. The quantum world is uncertain but beautifully structured. The rules had changed forever. Certainty was replaced by probability. While electrons puzzled some, others probed the atom's core, the nucleus. Einstein's E-MC2 revealed mass and energy are interchangeable. Inside the nucleus, protons repel, but the strong nuclear force binds them, barely, in large atoms. In unstable atoms like uranium, the nucleus can split, nuclear fission, releasing huge energy as mass converts to energy. This chain reaction powers nuclear plants and bombs. The sun uses fusion, smashing small atoms together to make bigger ones, releasing even more energy. Fusion powers the stars and could be the future of clean energy. Both fission and fusion turn tiny amounts of mass into vast energy. The secrets of the nucleus unlock the power of the universe. We learn to harness the energy of stars. The atom's heart was no longer a mystery. Mass and energy were two sides of the same coin. The nuclear age had begun. Quantum discoveries didn't just explain the universe, they built our modern world. The key semiconductors like silicon, which can be tuned to conduct or block electricity. In solids, billions of atoms' energy levels merge into bands. Conductors have overlapping bands. Insulators have a big gap. Semiconductors have a small gap. Doping silicon with impurities creates N-type, extra electrons, and P-type, holes materials. Joining them forms a PN junction, a diode, a one-way gate for electricity. Combine these, and you get a transistor, a tiny switch that can turn on and off billions of times per second. Transistors are the building blocks of computers and all digital devices. Quantum rules of electrons power the information age. Every smartphone, computer, and network relies on this quantum trickery. The digital world is built on quantum foundations. The quantum revolution became a technological one. Our lives are shaped by quantum mechanics. The first quantum revolution gave us transistors and lasers. Now we're entering a second. Quantum computing. Classical computers use bits, zeros or ones. Quantum computers use qubits, which can be 0, 1, or both at once, like a spinning coin. This superposition lets quantum computers explore many possibilities simultaneously. With just a few hundred qubits, you could represent more states than atoms in the universe. Quantum computers aren't just faster, they're fundamentally different. They could revolutionize chemistry, logistics, and cryptography. But qubits are fragile. The challenge is keeping them stable. Progress is rapid. Machines with hundreds of qubits are being built. We're learning to harness probability clouds for computation. The quantum future is being built now. The rules of the universe are becoming our tools. The next revolution is underway. Modern physics is a journey from certainty to a new, deeper understanding. It began with a glowing metal that broke the old rules. We learned light is both particle and wave. Atoms are mostly empty, and the universe deals in probabilities. Uncertainty isn't a flaw. It's fundamental. From this, we built nuclear power, semiconductors, and the digital world. Every modern technology owes its existence to quantum discoveries. The story isn't over. A new chapter is beginning. The first quantum revolution explained the world. The second will let us control it. Quantum computing could solve problems once thought impossible. This is the story of human curiosity, asking why and daring to find out. The universe is stranger and more wonderful than we imagined. The quantum realm is our reality's operating system, and we're learning to write the code. The future is uncertain, and that's what makes it exciting.